Ok, continuamos con el workshop número 3, creado para honrar a nuestros estudiantes de doctorado. Welcome, Professor Sarathy. Thank you so much for staying with us. I am going to introduce you to the audience. Professor Sarathy is the new invited here. He is an associate professor of chemical engineering and associate director of the Clean Combustion Research Center at KAUST University in Arabia. Dr. Sarathy was previously a postdoctoral research in the combustion chemistry group at the United States Department of Energy Lawrence Livermore National Laboratory. He received his PhD and master's degree in environment and chemical engineering at the University of Toronto, and his bachelor is in environment engineering chemical specialization from University of Waterloo. Dr. Sarathy was named a Clavierite analytic high-seated researcher. His research interest is in developing sustainable energy technology with decreased net environment impact. A major thrust of his research is using chemical kinetic simulation to design fuel engines and reactors. Dr. Sarathy, thank you so much for help to our university and our country and for receiving our students in your institution. Welcome to our university. Thank you so much. You have your audience now.
Okay, muchas gracias, Professor Farid. And buenos dias, everybody. My name is Mani. I'm connecting to you from Saudi Arabia, and I'll talk a little bit more about the research that I do here at the Clean Combustion Research Center. As Professor Farid had mentioned, my expertise is in chemical kinetics. And I'll talk to you a bit about chemical kinetics of complex systems. And of course, the types of systems that I'm interested in are particularly specific to energy generation, like systems for combustion to create power for airplanes, for marine application, and for automobiles. So this is the map of where I am. I'm here in Saudi Arabia. I hope you can see it. And in Saudi Arabia, we're near a city called Jeddah. And just to look a bit closer, this is the city of Jeddah. Many people know the place Mecca. It's very famous for many people in the Islamic religion. So we are not too far from Mecca, and it's a very nice place. It's on the coast near to the Red Sea. Now today is March 18th, and it's already 30 degrees Celsius outside. So it's quite hot, even in March. But this is nice weather for us. In the summer, it will become very hot here. So I'll be talking to you about chemical kinetics. And if you have not studied chemical kinetics before, you should understand that the Nobel Prize in Chemistry was awarded in the field of chemical kinetics in the year 1956. So about 70 years ago, a Nobel Prize was awarded in this field to two scientists. One was a British chemist named Sir Hinshelwood, and the other was a Russian chemist named Semenov. So together, Hinshelwood and Semenov were co-awarded the Nobel Prize in Chemistry in 1956 for their work on chemical kinetics. And in his speech to the Nobel Committee when he got the award, this is a quote from Dr. Sir Hinshelwood. He says, "Nobody, I suppose, could devote many years to the study of chemical kinetics without being deeply conscious of the fascination of time and change. This is something that goes outside science into poetry. but science, subject to rigid necessity of always seeking closer approximations to the truth, itself contains many poetical elements. And then he goes on to say there's many ways in which the mysteries of chemical change might begin to impress themselves on a young chemist. So you can see already, chemical kinetics is a very rigorous science, but even the pioneers in this field thought of it also like poetry. And that's why I like this field. You will find that there's a lot of artistic element to it, but also very fundamentally sound scientific elements. So in my team, I try to apply this knowledge of chemical kinetics to study very complex processes, things such as combustion inside of engines, catalytic reactors, and even chemical processes happening in the atmosphere. But for today, I'll focus mainly on combustion engines and different kind of fuels. So many of us will think, what is the future of engines? What is the future of fuels? And what is the future of energy? 100 years ago, the automobile just started to become very popular, and gasoline and diesel fuels started to become prominent in society. Nowadays, everything is powered by gasoline, diesel, jet fuel, and many different types of hydrocarbons. And much of these hydrocarbons are coming from places like Saudi Arabia. In your country also, you have oil producing regions and other parts of South America. But what about the future? 10 years from now, 20 years from now, 50 years from now, what is the future of the fuels and energy? I think it's an important question to ask if we want to do research in this area. These are some projections. Even in the next 20 years, there's still a projection that 85% of energy used in transportation will be met still by oil. That means for ships and airplanes, and also for trucks and cars, it's going to be hard to move to other kinds of energy sources in the next 2 decades. It will take even longer than 20 years. One of the major reasons for this is because the global population is increasing about 15% in the next 10 years, and many of the younger population coming in the next 10 years will require mobility by the year 2040. So there's an associated increase with the transportation demand. And important also to note is the size of economies are growing. I'm sure the Colombian economy is growing. Similarly, many economies in Asia, like China, India, parts of Africa, are growing very quickly. And with this growth in GDP will come an increased demand for transportation and increased demand for energy. So in CAUS, what we try to understand is if we are to meet the energy demands for the future, what is the best fuel to be used? And what are the best kinds of engines that we should be operating? And we have developed a consortium of industry partners and some academics as well to look at different types of fuels and engines. We look at heavy duty sector like trucks and trains. We look at light duty vehicles like passenger vehicles. We look at aviation sector and the role of biofuels in aviation, and also in marine applications like large ships. If we look at the transportation sector, such as vehicles, trucks, and passenger cars, many countries, especially in Europe, are thinking that electrification will be the solution to deal with carbon emissions, also the solution to deal with the increased demand for transportation. But there's lots of research now that's showing it will be difficult to fully electrify using battery electric vehicles, all of the vehicles in the world today. And the main reason for this is you cannot just have battery electric vehicle, you also have to have renewable energy grid. And if you need both of these things, you need lots of mineral resources. These two graphs show the types of minerals that you need: iron, aluminum, copper, nickel, chromium, indium, neodymium, lithium, lead, zinc, dysporium. All of these minerals need to be obtained from mining resources, mining reserves. And on the y-axis, you see that the demand for these minerals in the next 30 years will be about 3 to 5 times greater than the production that has been there in the year 2000. So in order to get all of these chemicals at the scale that we need them, we need to grow the mining industry by about a factor of 5 in the next 20, 25 years. And this is very challenging. Furthermore, if you see on the right side, the reserves, the known reserves for all these minerals, for many of them, the known reserves are lower than the demand. And for some of them, the reserves are available, but we need to exploit those reserves. So we need to put a lot of investment. And at present, the investments are not being made at the same scale at which the growth or increase in demand will be needed. So even though I am optimistic for battery electric vehicles, I think they are necessary. I'll show you later I'm very optimistic about renewable energy also. But for both of these to increase at a pace related to how we need energy demand, we need a lot more investment, and currently those investments are not being made. And the more we delay these investments, even further up, we'll push out these targets for having electrified solutions. So it's unlikely to happen in the next 20 years, given the current level of investment and growth in the supply chain. So for that reason, I believe internal combustion engines are not dead. Internal combustion engine will continue to play a role in powering vehicles, aircraft, marine vessels, well into the year 2040 and 2045. And of course, many of these engines will become smaller. The battery electric powertrain or the hybrid vehicle, the hybridization will become more dependent on the electricity, but the engine will still be there. The engine will just become less important as time goes on. And eventually, maybe by year 2045, we will get rid of the engine completely. But just thinking that the engine is dead today is not an appropriate solution, and not investing into technology development in engines for the next 20 years will just lead to more carbon emissions and more negative impacts. So a lot of the work we do at KAUST is to ensure that engines for the next 20 years will continue to be even lower emitting. They will be able to operate on different types of fuels, and they will result in lower carbon emission. So in order to optimize the engine, we need to think about two things. We need to think about, of course, the engine operation, and then we also need to think about the fuel. And that's my main job. My main job is to look at how we can optimize the fuel and the engine to give you the best performance in terms of efficiency, which means lower carbon emission, and also in terms of lowering the harmful emissions that are coming out of the engine. So I look at the engine as a reactor. The reactor has fuel and air. These things go into the engine, they react, and then you have a thermodynamic energy generation process, which eventually produces some CO2 and water, but also some harmful intermediates during the process. And my goal as a scientist is to use fundamental knowledge of transport, thermodynamics, and reaction kinetics so we can optimize the fuel and the engine together. And if you see the kind of research that we do here, we look at all aspects related to fuels and engines. So we start at a very fundamental level, even understand what is the fuel made of, what are the different hydrocarbons that are there, how can we mix them together to give a better fuel. We characterize those fuels at a molecular level. Then we conduct experiments in our laboratories here to understand how different molecules will react with each other and how we can predict that reactivity. We enable reactor simulations so we can predict how fuels will behave under different environmental conditions. And then we develop tools that we give to the industry. And we give these tools to industry so that they can optimize then their engine designs and their fuel formulation. And we have been doing this now at KAUST in the Clean Combustion Research Center for about 10 years, since the university opened in 2010. And my primary approach is what we call a simulation-based approach. I work with the experimentalist also, but most of my goal is to make it possible to have a predictive simulation of the combustion process. So it starts at a very fundamental level using chemical kinetics and thermodynamic models to predict how different molecules will behave. Then we do simplification of the kinetic models to couple them with computational fluid dynamics simulation, as we see here for a spray combustion process. And then eventually we further simplify the kinetics and perform full-scale engine simulation to understand how engines actually operate and what kinds of emissions are being produced. So today I'll mainly talk about the fuel side and what is the chemical kinetics of the fuel and how we can understand it. Now, you all are studying a lot about biomass and biofuels. I've studied a lot also about biofuels, and I'll talk a bit about that also. But to me, oftentimes more complicated than biofuel is petroleum fuel from a kinetic perspective. And the main reason is petroleum hydrocarbons are coming from crude oil. And when we bring the crude oil into the refinery, we distill it into different fractions. And each fraction has different types of molecules. And if we start with gasoline and naphtha, the number of molecules are maybe 100 to 200 different types of molecules. But if we go to jet fuel and diesel, we will have something like 300 to 500 different molecules. And if we look at the type of fuel oil that's used to power a large marine vessel used for shipping and cargo, you have sometimes 1,000 to 2,000 different species. And that makes it very difficult to develop kinetic models. And my goal is to enable the capability to model any kind of fuel, regardless of its complexity, using detailed chemical kinetics. Now, the same thing is true for biomass. Now, if you take sugarcane and you make ethanol, it's quite easy. I only have one compound to worry about, ethanol. That's my fuel. And I've done a lot of work making models for ethanol and other alcohols. Similarly, if you make biodiesel, biodiesel is a mixture of esters, fatty acid methyl esters. You only have about maybe 8 to 10 different kind of esters that are there. And that's actually quite simple, in my opinion. We don't have hundreds of compounds we have to worry about. However, if you take biomass and you pyrolyze it, which is the topic of Mr. Javier Loza, who will give his PhD defense today. If you take a biomass and you pyrolyze it, you get a bio-oil, and that bio-oil is very complex. It has maybe 400, 500, 600 different species, depending on how you do the pyrolysis. And then we have a system that I'm interested in. How do we study the kinetics of those very complex bio-oils? And what I will show you today is the process that we have developed for studying kinetics of petroleum are directly relevant to also studying things like bio-oils. So here's a typical example of what's there in different type of petroleum fuel. Gasoline, you have carbon number from about 5 to 9. You have different types of hydrocarbons here, branched alkane, linear alkane, cycloalkanes, aromatics. If you go to diesel, you have just longer chain hydrocarbons, but the same classes. And also in jet fuel, somewhere between C9 and C14, similar types of classes of hydrocarbons. And the goal is to understand how these mixture of hydrocarbons behave inside of engines. The current approach in combustion is what we call surrogate fuel modeling approach. If you go to the combustion community today, this is the state of the art. We take a surrogate of the entire fuel, and then we try to model that surrogate. A surrogate is a mixture of about 5, 6, sometimes even 10 components, which represent the real fuel. And in this example here, we can see here for a typical diesel fuel, or a gasoline fuel for that matter, how we can choose different components to make a surrogate. So I can choose maybe 2 different types of aromatic species. I can choose a few cycloalkanes and an alkene. I can choose some normal alkanes and then some branched alkanes. And then I mix these things together and I have a surrogate. And then I develop kinetic model for all of these molecules and to understand how the mixture behaves. Now, this is a good approach. This is the approach I did for many years when I was in Lawrence Livermore National Laboratory, and also since I came to KAUST. And we've developed maybe 50, 60 different types of kinetic models for different fuels. But the challenge with this approach is that I always, whenever I have a new component I bring into the surrogate, I need to make a new kinetic model. And sometimes if I take one gasoline and I measure the composition, and then I go to a different gasoline and I measure its composition, I cannot use the same surrogate components. So we know the process works, but the process is kind of challenging and very time consuming. So I started to think about 5 years ago, can we rethink this whole approach to understanding how mixtures behave? And can we come up with a new way in which we understand surrogates and a new way in which we can study the combustion and kinetics of a fuel? And instead of then looking at different molecules that we see here in a typical approach, I started to think of, let's design the surrogate based on the functional groups. The functional groups are things like the number of paraffinic hydrocarbon sites, like the CH3 groups, or the number of secondary CH2 groups, maybe the number of aromatic rings in the mixture, or the number of cyclics as well. So like this, we started to develop a surrogate formulation approach that did not think about the components in the fuel. Instead, it thought about the functional groups that are in the fuel. And that's very different, because a hydrocarbon fuel, petroleum fuel, a bio oil, they might have several thousand different hydrocarbons, but there's only about 11 to 15 different types of functional groups. So if we look at things from functional group perspective, we don't have to worry about 1,000 different molecules. We only worry about, say, 15 different functional groups. And therefore, we made an approach we call minimalist functional group approach to surrogate modeling. And I'll show you some example of this. So here for the first example, I'll show you how just 5 functional groups, paraffinic CH3, paraffinic CH2, paraffinic CH, naphthenic CH, CH2, and aromatic CH, aromatic CCH, is enough to model any gasoline fuel that doesn't have ethanol. Just 5 functional groups. So to test this method, we use NMR, nuclear magnetic resonance spectroscopy. Specifically, we use proton NMR. And with proton NMR, we can take an oil sample or a fuel sample, we put it inside of the NMR machine, and we can directly measure the chemical shift associated with different functional groups. So that's shown on the right side. Depending on the spectral region, we can see the area of a peak in a specific spectral region, and we can correlate that directly with the quantity of a specific functional group. And on the right side, we just see some examples. For example, if I want to know how many paraffinic CH3s there are, I go into the spectra between 2 and 2.64, and I take the area under the curve, and I know exactly for a complex mixture how many paraffinic CH3s there are. And I can do this with gasoline, I can do this with diesel, I can do it with bio-oil, I can do it with petroleum, crude oil also. So for this example, we took 6 different gasoline fuels. So each of these spectra is a different gasoline. You can see they're all different. They have different spectra, which means they have different functional group distribution. Now, based on that functional group, I then formulated some surrogate that matched exactly or as close as possible the different functional groups in the real gasoline fuel. And the interesting thing we found is for one type of gasoline, and this gasoline, let's just call, for example, phase A, gasoline A, I can get all the different functional groups in the real fuel with just one molecule, as long as I choose the right molecule. And this molecule is a 2,4-dimethylpentane. It has some CH3 groups, 2 CH groups, and 1 CH2 group. And this molecule has the same functional group distribution as this very complex gasoline with about 120 components. Similarly, if we look at gasoline F, we need 2 different components, 3-methylpentane and indane, but they also match the functional group distribution of the real fuel. And similarly for phase G, I have these tetralin and 3-methylpentane. So like this, for each fuel, we have to choose a different molecule, but this molecule represents all of the functional groups inside of the real fuel. And just to prove that, on the x-axis here for each fuel, A, C, F, G, I, J, for each fuel, I have one of the 5 functional groups, paraffinic CH3, CH2, CH, and so on. And then the weight percent for the real fuel in black, which is measured by NMR, and then the surrogate, which I can calculate exactly because I know the mixture. And here we can see for most of these fuels, we have a very good match, plus or minus 5% difference in the functional group matching. So this method shows that I can match the functional group without needing so many components. I don't need 5 components or 10 components or 15 components. All I need is sometimes 1 or 2 components. Now the next question is this mixture or this 1 component or 2 component, is it good enough to match the kinetics or the combustion properties of the real fuel? So that's what we tested next. We took the real fuels, the different gasoline, and we took our mixtures, these very simple surrogates for each fuel, and we put both of them in an ignition quality tester. It's a device which measures the ignition delay time under diesel engine-like conditions. And in this case, we operate this ignition quality tester around 21 atmospheres and 835 Kelvin, and we measure on the x-axis the ignition delay time, which is denoted by an increase in pressure at some period of time. And we can see here for every gasoline in the red, the surrogate in the blue matches very closely within 1 or 2 milliseconds the ignition delay time. You can see for one gasoline, we have very good match. For phase G gasoline, the surrogate in the blue and the gasoline in the red, less than 1 millisecond difference. And like this, for all the tests we did, we was very remarkable. We found that just one component, if it's chosen correctly, can reproduce the ignition delay time for a very complex gasoline with hundreds of components. And then we did some other measurements of ignition delay time in a rapid compression machine. It's another type of device for measuring the ignition delay time for fuel-air mixtures. And here also we see the real gasolines in the purple, and the blue is the surrogate. For all of these different gasolines, we found a very good match in the rapid compression machine ignition delay time measured at stoichiometric condition and 20 atmosphere. So all of this showed that even experimentally, this idea of having a functional group approach to represent a real fuel is valid. The experiments are showing it. This is not theory. We're doing the experiment, we're demonstrating it. There's no theoretical assumptions being made here. But we know the theory as well, because now we are able to develop kinetic models for these different surrogates. We're able to identify all the reaction mechanism, and we can explain exactly why this approach works. And I won't go into the details of it. For that, I'm happy to have further discussions with you, or I can also share the papers. We have about 20 papers now on this topic to clarify how this approach works. Now, the next question is, can we take this approach and apply it to much more complex fuels, not just gasoline or diesel? And in this case, we're demonstrating that we can even do it for a heavy fuel oil. Heavy fuel oil has about 2,000 different species. I can make one molecule for a heavy fuel oil, which represents completely the functional group distribution. And with this molecule, I can start to predict combustion properties. I can predict also thermodynamic properties, physical properties like boiling point, melting point, critical temperature, critical pressure. And Mr. Javier Loza, who will defend his PhD later today, has also visited KAUST, and he has studied our approach, and he has adopted it for studying the thermophysical and combustion properties for bio-oil derived from sugarcane bagasse. So he is one of the first to demonstrate that this approach of understanding functional groups is relevant also to biomass type derived fuels, which also are very, very complex. The only difference there is we will use a different set of functional groups, because when you look at bio-oil, you will have oxygenated functional groups as well, like aldehydic, alcohol, and so on. And those types of functionalities need to be studied when you go to a bio-oil as opposed to a hydrocarbon fuel. Now, the next question I had is, if I can develop kinetic model and study kinetic models for these very simple surrogates, I apologize. If I can study the very simple surrogates and kinetics using very simple approaches and functional groups, can I develop a different approach? And in this case, a machine learning approach, or a purely data-driven approach to the prediction of the combustion kinetic properties. So using that same knowledge of functional groups, instead of now developing a surrogate and a kinetic model, I thought, can we train a machine learning model to predict the combustion properties? So I'll show you some approach for this. Essentially, I'll show you how we can predict things like the cetane number and the octane number from the functional groups that are in the fuel using a machine learning model. And in this case, we're using what we call artificial neural network-based model. Essentially, this is just a different type of quantitative structure property relationship model, where we say QSPR model. So here what we do is we take as inputs to our model the different functional groups, paraffinic CH3, paraffinic CH2, CH, and so on. We also require the molecular weight of the fuel mixture, which you can obtain from the distillation curve. And also we got a parameter we call the branching index, which is described in our paper in 2016, if you're interested about this specific parameter. Then we took a database of about 120, 130 different cetane measurements, and we trained a model. We trained a model to predict what is the measured cetane number based on the inputs of the different functional groups. And after that, we then took NMR spectra for real fuels, and for a number of real fuels, about 20 different real fuels, we measured the NMR spectra, and then we determined if the model that we made could be able to predict the cetane numbers of those real fuels. This model is available on our website. You can visit and try it out, cloudflame.caus.edu.sa. And here we show for 22 real fuel mixtures, gasoline, diesel fuels, and another 60 blends where we just blended different hydrocarbons and measured the cetane number. Our model is able to predict the DCN very accurately. You can see the correlation between predicted and measured DCN for real fuels and for blends was very good. And again, the only inputs to the model is the functional groups. You don't need to know what types of components there are. You just need to know the functional groups and the average molecular weight of the mixture. And here, the previous example was showing an MLR, multiple linear regression-based model. Here I'm showing a model based on artificial neural network, and also with the addition of alcohols and ethers. So we took a lot of different alcohols, from ethanol all the way up to isomers of butanol, as well as different types of ethers, dimethyl ether, dibutyl ether, and we blended them with hydrocarbons and added them to the database, and also we were able to get a very accurate model with a correlation of about 0.95. And we've also tested this model now for research octane number and motor octane number. So with 7 different functional groups and the molecular weight for a database of 281 fuels for which we have RON and MON, we got a very nice model, correlations above 0.99 for the machine learning based model. And furthermore, we recently extended this now to 500 different fuels, cetane number measurements. So it goes to show that whether it's a kinetic model, whether it's a machine learning model, the functional groups are what matters. So we can stop thinking about kinetics as a field that's very complex, where you need to understand every single molecule and how it behaves. Really, kinetics is much simpler. As long as we understand the behavior of functional groups, we can make very accurate predictions. And recently, we started to show we don't only predict combustion properties, we can also predict the thermodynamic property, like the heat of formation, the entropy of formation, the heat capacity. So we're now using just functional group approach to predict any type of thermophysical property of pure molecules or mixtures. And traditionally, how we would do this is using group additivity. And this figure shows that we're able to beat group additivity. Group additivity would typically have errors of about 3 kilocalories per mole for different branched hydrocarbons. Our results are showing that our machine learning model, in this case, support vector regression model, has uncertain errors of less than 1 kilocalorie per mole. Now, the last part of my presentation is to talk about some new kinds of fuels that we are interested in studying. not just petroleum fuels and biomass-derived fuels. Besides these, there's a large interest in the kingdom now to make fuels that are coming from CO2 and hydrogen. The general concept here is that we can take sun, large amount of solar energy to split water and to make hydrogen. We can react that hydrogen with nitrogen and make ammonia and use that in vessels. Also, we're interested in taking CO2 from the air and reacting that with hydrogen to make hydrocarbons, which can be used for aviation application, similar to what plants do, but by means of making biofuel. We want to use industrial process reactors to convert CO2 and hydrogen to liquid hydrocarbons. So you may have heard of these concepts. We call them power to X. We take renewable energy like solar and wind. We split the water. We react to the hydrogen with CO2. And then we make liquid hydrocarbons or liquid fuels, which can be used for carbon neutral transportation. So just to give you an overview, the kinds of things I'm working on, we're working on methanol, trying to improve the production process of e-methanol from renewables, production of ammonia and the combustion of ammonia. Ammonia, we think it's good because we already have ships that are capable of transporting ammonia for fertilizer industry. So we can also use this to power the ship engines. We currently have a very big project in Saudi Arabia for ammonia production from renewable electricity. By year 2026, we will have the largest green ammonia plant in the world, and that's being built in the northern part of Saudi Arabia. In addition, we're trying to also make gasoline and diesel directly from CO2 and hydrogen using what we call methanol to gasoline process or Fischer-Tropsch-based synthesis. And recently, a fuel that I'm also interested in is formic acid. Formic acid can be made from taking CO2 and hydrogen and reacting them together. And formic acid has a molecular formula HCOOH. It's shown here at the bottom, HCOOH. So we have started to measure things like the laminar flame speed for formic acid, the ignition delay time, and we're starting to understand the kinetics of this fuel. And our general idea is that we can take formic acid, produce it from CO2 and hydrogen, and then blend that in with either gasoline or diesel and use them inside of combustion engines. So there's a few papers here. One paper is I recently published in Energy and Fuels. If you're interested in formic acid as a renewable e-fuel, you're free to read that. And I can also share with you some more recent papers that have come out in the last 4 months. So I'd like to thank you, everybody. Muchas gracias. And I'd be happy to take any questions from the audience.
Thank you so much for great conference, Professor Sarathy. See? I understand that all the knowledge about the surrogate, this complex molecule, but it's very important for doing some specific study relating to this molecule complex. But I have some questions, excuse me. So, one question is from Javier Ordóñez. The proposed surrogate expresses the chemical characteristics, but does it also express the physical properties?
Yeah, it's a very good question. So the problem with this kind of surrogate right now is it's mainly limited to the gas phase combustion property after the fuel has vaporized. So the question is, when you have a mixture with many different hydrocarbon, can this surrogate reproduce the physical property, like the spray, droplet size diameter, droplet size distribution, maybe the boiling distillation curve? And the answer to that is no. In order to reproduce things like a distillation curve you need to have multiple components. Now, that's not necessarily a problem, because in CFD codes anyways, we currently use the approach that we have a physical surrogate to represent the physical properties which influence the spray breakup, droplet size distribution, evaporation, and then the chemistry happens in the gas phase. Now, this is how a typical CFD for an engine simulation happens. Now, where it becomes problematic is if you have your bio-oil droplet and then you have reactions happening in the liquid phase. Then I think we have to think, how do we accommodate? Because then if the liquid itself is reacting and maybe it's cracking into smaller components, how we approach the modeling will have to be a bit different. And there I move actually away from, we have now 2 papers in combustion and flame, where we move away from even having one surrogate. So before, what I present to you today is that the surrogate has some molecular structure and it represents the real fuel. But now we recently abandoned the idea completely that you have a surrogate and you have a kinetic model for the surrogate. Now what we have is this kinetic model only for the functional group. So we call this functional group approach or functional group mechanism. I'm happy to share the papers with you. And what this approach allows now is there's no surrogate. All we have is kinetics of how different functional groups react with each other. So this we can easily implement even for liquid phase reactions. So you would have one physical surrogate, and then you would have a kinetic model for just the functional group reactivity.
Thank you. We have another question from Camilo Uribe. Can this minimalist kinetic approach be used to estimate other combustion properties such as emissions?
Yeah, definitely. So what I did not show you today, and we have a paper now in Energy and Fuels about this, is we can predict also the combustion intermediate. We have measured this in a jet-stirred reactor. So we've measured the intermediate and also the final product emission. And the model, this type of approach, functional group approach and minimalist approach can predict also emissions. And even also soot formation we can do.
Thank you, Professor Sarathy. We have another question coming from Jesse Osorio. Do you know if this approach, functional groups, is applicable to more complex mixture like pyrolase or lignin oils? And what would be the limitation when applied to these systems?
Yes, it's a very good question, Jesse. So the answer is yes, it can be applied. The limitation is you need to define new functional group, because pyrolysis and lignin oil will have different type of functional group. But in the biomass pyrolysis literature, these functional groups are already being well understood. And I have some colleagues that I'm working with. If we have a bio-oil and we measure the functional group, yes, we should be able to predict the combustion property. But what is more challenging is from the biomass, can we predict the bio-oil composition? And this is also a problem we're trying to work on now. From the biomass, if we know the functional groups of the biomass, can we predict then the pyrolysis products that are being made? And Javier Loza, who's presenting later today, his thesis, his work also helps to advance this understanding. But I think we need to work more. It's relatively new area we're looking into.
Thank you, Professor Sarathy. There are another question from Valentina Sierra. She said that, thank you for sharing your research, and it's really interesting. Do you think that this methodology could be applied to obtain the biochar gasification kinetic model?
So for biochar gasification, yes, biochar is I'd say it's much more. It's not a very it's not very much like you have many different types of compounds, but yes, biochar you have a complex structure with different types of functional groups. And indeed, it would be similar to a coal combustion model. So I would say yes, the approach is valid. For biochar, again, typically in the literature, you would not find the surrogate approach being used. You would not be mixing different molecules. Typically, they will just come up anyways with some representative structure for the biochar and study the kinetics of that. And the group that is very good at this is in Politecnico di Milano, Professor Ranzi, Eliseo Ranzi, Professor Tiziano Faravelli. They have done a lot of work in gasification for biochar, plastics. So that and their approach is very similar. They use functional groups to characterize the particulate, and then they develop the kinetic model. But I'm not working so much in the solids combustion. It's I think there you have a lot of reaction also happening in the solid phase, which you need to characterize, and it's not my area of focus.
Thank you, Professor. There are another two last questions. One is coming from Diana Caroline. What could be the real improvement of using formic acid blend?
So the advantage of formic acid is we can make it from CO2 and hydrogen. So if we can split water with renewable energy, which has about 80% efficiency today, then you can react that hydrogen with CO2 that's captured from either the air or from some cement plant to make formic acid. Now the formic acid is then carbon neutral. Once you burn the formic acid, you will release that CO2 again. But if that CO2 initially came from air, then it's a carbon neutral fuel. Now, the problem with formic acid is you have a low energy density. It's about 1/5 of gasoline. So you will need to carry much more fuel in the vehicle. And also, it does not burn very well. So you need to do something to help it to burn. So that's why we're saying if you can have a mixture of about 70-80% formic acid and 20% gasoline or diesel, the mixture will burn well. But you still got rid of 80% of the carbon emission. So formic acid could be one option. Methanol is another option. So there'll be different types of e-fuel that are coming from CO2 and hydrogen that will be interesting in the future. And these are then going to be, you can say, mixed with biofuel. I think the future market will have always some mixture of biofuel, e-fuel, and hydrocarbon fuel. And as we go into beyond 2030, I think hydrocarbon from petroleum will decrease. You'll have more biofuel, more e-fuel, and eventually all of the petroleum fuel will have to go away. You'll only have biofuel and e-fuel. And maybe in the very long distance, I say 2050 afterwards, maybe everything will only be hydrogen and electric. So I think we're in this roadmap to get there.
Thank you. The last question is coming from Miriam Rojas. What do you think about the use that should be made of hydrogen, blue or green, to improve poor fuels or to synthesize ammonia?
So I think both. I think both are important. So and this project that we have in Saudi Arabia, in the northern part of Saudi Arabia, is called NEOM. We make green hydrogen. Our main focus is green hydrogen. But we cannot use green hydrogen everywhere. That's a fact. within NEOM, we're developing an infrastructure to have a filling station for hydrogen, fuel cell electric vehicle, but we cannot have all the ships in the Red Sea running on hydrogen. So we are working on program to blend hydrogen with diesel on ships, so you can fire at least 30-40% hydrogen with diesel. So I think that goes to your first point, using hydrogen to improve poor fuels. I think this is an important area, but it's limited for us because this is then only the local use of hydrogen. In Saudi Arabia, we want to export the hydrogen to Europe. We want to export it to Japan and to Korea, because that will be a source of revenue for Saudi Arabia once oil is no longer valuable. So when we want to export hydrogen, the best option is ammonia, because you cannot transport hydrogen over long distances very efficiently and cost effectively. So we are building a green ammonia production facility only for the reason to sell that green ammonia to Europe and to Japan. And then because of that, we also work on projects for the combustion of green ammonia, because in Japan they're interested in directly burning the ammonia rather than converting it back to hydrogen and using it. So I think both things are important. It depends on what is your goal, local use, or if you want to do export or long distance transport of hydrogen.
Professor Sarathy, thank you so much. Only one last statement for reflection for the future is that physical property need and group and set of group, different group molecular, complex molecular, but the chemical property maybe with individual molecular is necessary to understand the chemical property. This is one statement for the reflection. Thank you so much, Professor Sarathy. Thank you so much for help us, for improve our PhD program, to receive our student in your institute. So I would like to see you in the next future as soon as possible. Thank you so much.
Okay.